Good morning. Today we are going to discuss about eddy current and self-induction. Let us do the numericals on self-inductance. The formula used are flux phi is equal to Li or phi is equal to NLI for capital N turns. Induced EMF E is equal to minus L into di by dt. In case of a solenoid, capital L is equal to mu naught small letter n square A into L, where small letter n is the number of turns per unit length. The units used are flux in Weber, EMF in volt, current in ampere, self-inductance L in Henry, length in meter, area of solenoid in meter square. The value of mu naught is taken as 4 pi into 10 power minus 7 Weber, ampere raised to minus 1, meter raised to minus 1. The first question is, current in a circuit falls from 5 ampere to 0 ampere in 0.1 second. If an average EMF of 200 volt is induced, give an estimate of the self-inductance of the circuit. So, it is given that the current falls from 5 ampere to 0 ampere. Hence, the change in current di will be equal to final current minus initial current, that will be 0 minus 5 ampere. And the corresponding time is 0.1 second. Therefore, di by dt can be written as I2 minus I1 by t, that will be equal to 0 minus 5 divided by 0.1. On substituting, we get di by dt is equal to minus 50 ampere per second. Also, EMF is given as 200 volt. We are asked to calculate the self-inductance capital L of the circuit. So we know the formula. Magnitude of induced EMF E is equal to L into magnitude of di by dt. Therefore, L is equal to magnitude of E divided by magnitude of di by dt. Substituting EMF E as 200 and di by dt as 50, we get L is equal to 200 divided by 50, that is equal to 4 Henry. The next question is, current in an inductance of 1 millihenry is reduced from 5 milliampere to 0 in 1 millisecond. Find the EMF induced. So, it is given that self-inductance L is equal to 1 millihenry, which is equal to 1 into 10 power minus 3 Henry. The change in current is di is equal to 0 minus 5 milliampere. That will be equal to minus 5 milliampere or minus 5 into 10 power minus 3 ampere. Corresponding time dt is 1 millisecond or 1 into 10 power minus 3 second. We are asked to calculate the induced EMF. So, using the formula E is equal to minus L into di by dt, we get E is equal to minus L is replaced by 1 into 10 raised to minus 3 into di is replaced by minus 5 into 10 power minus 3, dt is replaced by 1 into 10 power minus 3. Therefore, on solving, we get EMF E is equal to 5 into 10 power minus 3 volt, that is equal to 5 millivolt. The next question is, what is the self-inductance of a solenoid of length 0.5 meter, area of cross-section 0.005 square meter and total number of turns 1000. So, it is given length of the solenoid is small letter L is equal to 0.5 meter. Area of cross section of solenoid is 0.005 square meter, and total number of turns capital N is equal to 1000. So we can calculate number of turns per unit length, that is small letter n. Small letter n is equal to capital N by L, that can be written as 1000 divided by 0.5, that will be equal to 2000. Thus, self-inductance of a solenoid is given by the formula capital L is equal to mu naught small letter n square into A into L. On substituting the values, we get self-inductance capital L is equal to mu naught is replaced by 4 pi into 10 raised to minus 7 into small letter n is replaced by 2000, so 2000 square, into capital A is replaced by 0.005 into small l is replaced by 0.5. On substituting, we get the final answer as 0.025 Henry. The next question is, an EMF of 250 volt is induced in a coil when current in it changes from 10 ampere to 6 ampere in 0.4 seconds. What is the self-inductance of the coil? So, it is given that induced EMF E is equal to 250 microvolt, that can be written as 250 into 10 raised to minus 6 volt. The change in current is given by dI is equal to 6 minus 10, that is equal to minus 4 ampere, and the change in time is dt is equal to 0.4 seconds. We are asked to calculate the self-inductance capital L. So we can use the formula modulus of induced EMF E is equal to L into modulus of di by dt, or L is equal to modulus of induced EMF E divided by modulus of di by dt. Therefore, by substituting, we get L is equal to E is replaced by 250 into 10 raised to minus 6 divided by modulus of di by dt is replaced by 4 divided by 0.4. So, on solving, we get L is equal to 25 into 10 raised to minus 6 Henry. The next question is, find the change in current in an inductor of 10 Henry in which the EMF induced is 300 volt in 10 raised to minus 2 seconds. Also, find the change in magnetic flux. Here it is given that L is equal to 10 Henry, EMF E is equal to 300 volt, the time dt is equal to 10 raised to minus 2 seconds. We are asked to calculate the change in current di as well as the change in flux d phi. So, we have the formula induced EMF E is equal to L into di by dt when we take the magnitude. Therefore, E is replaced by 300, L is replaced by 10, di we have to calculate, dt is replaced by 10 raised to minus 2. Therefore, 300 is equal to 10 into di by 10 raised to minus 2, or di is equal to, on cross multiplying, we get 300 into 10 raised to minus 2 divided by 10. That will be equal to 0.3 ampere. Therefore, the change in current, we got it as 0.3 ampere. The next one is find a change in magnetic flux. We have the equation induced EMF is equal to d phi by dt. Therefore, d phi is equal to E into dt. That will be equal to E is replaced by 300 into dt is replaced by 10 raised to minus 2. So calculating, we get d phi is equal to 3 Weber. Next is the self-inductance of a coil having 200 turns is 10 millihenry. Compute the total flux linked with the coil. Also, determine the magnetic flux through the cross-section of the coil corresponding to current of 4 milliampere. So, here it is given the total number of turns capital N is equal to 200. The self-inductance capital L is equal to 10 millihenry. That is equal to 10 into 10 power minus 3 Henry. Current I is equal to 4 milliampere. That is equal to 4 into 10 power minus 3 ampere. First, we have to calculate the total flux phi linked with the coil. So, we know the formula. The total magnetic flux linked with the coil phi is equal to capital N into capital L into capital I. Therefore, phi is equal to N is replaced by 200 into L is replaced by 10 into 10 power minus 3 into I is replaced by 4 into 10 power minus 3. On calculating, we get the total flux phi is equal to 8 into 10 power minus 3 Weber. Also, now we have to determine the magnetic flux through the cross section of the coil. Therefore, the magnetic flux through the cross section of the coil is equal to magnetic flux linked with each turn. Therefore, we get the magnetic flux through the cross section of the coil is equal to total magnetic flux linked with the coil divided by total number of turns, or phi by N. Therefore, the magnetic flux through the cross section of the coil is equal to phi is replaced by 8 into 10 power minus 3 by N is replaced by 200. On substituting, we get that is equal to 4 into 10 power minus 5 Weber. The next question is, a solenoid of radius 3 cm and length 1 meter has 600 turns per meter. What is its self-inductance? Will the value of self-inductance change if it is wound on an iron piece? So, it is given radius of the solenoid, small letter r is equal to 3 cm, or that is equal to 3 into 10 power minus 2 meter. Length of the solenoid, small letter L is equal to 1 meter, and number of turns per unit length, that is small letter n, is given as 600. We are asked to calculate the self-inductance capital L. So, the formula for self-inductance of a solenoid is L is equal to mu naught small n square into A into L. So, we need to first calculate the value of A. That is area of the solenoid. A is equal to pi r square. That will be equal to pi into radius is replaced by 3 into 10 power minus 2 whole square. That will be equal to 9 pi into 10 raised to minus 4 meter square. Therefore, substituting the value, we get capital L is equal to mu naught n square AL becomes mu naught is replaced by 4 pi into 10 raised to minus 7 into n square is replaced by 600 square into A is replaced by 9 pi into 10 raised to minus 4 into L is replaced by 1 meter. So L is equal to 4 pi into 10 raised to minus 7 into 600 square into 9 pi into 10 raised to minus 4 into 1. On solving, we get it as 1.28 into 10 raised to minus 3 Henry. The second part is, will the value of self-inductance change if it is wound on an iron piece? If the solenoid is wound on an iron core, the value of the self-inductance will change.
Hello students, today let us learn the numericals on mutual inductance. Before we see what the question is, let us see what the formula is we have studied, and we will just revise how the formulas can be rewritten in different forms. First formula is for a mutual inductance of two coils, coaxial solenoids. We have seen that M is equal to N1 N2 L mu naught pi r square. So if we substitute N1 is equal to capital N1 by L, N2 is equal to capital N2 by L, we will be getting the following equation. Capital M is equal to capital N1 divided by L, capital N2 divided by L into L mu naught pi r square. Here one of the L cancels out and the expression that remains is M is equal to capital N1 capital N2 into mu naught pi r square, the whole thing divided by L. Here pi r square is your area, so we will be replacing it by A. The next formula that you have to remember is this. From Faraday's law of induction, we have learned that EMF is equal to minus N d phi b divided by dt. We have also learned from mutual inductance that term N d phi by dt is equal to M into di by dt. So comparing those two equations, we can write EMF is equal to minus M di by dt. So here are the few formulas that we have learned in mutual inductance and comparing it with EMF. So these two formulas, we will be using it in our numericals. Let's begin with. Let us see the first question. A conducting wire of 200 turns is wound over and near the center of a solenoid of 100 centimeter length and 2 centimeter radius having 600 turns. Calculate the mutual inductance of the two coils. So there is a solenoid of 100 centimeter length, 2 centimeter radius and 600 turns. Over this solenoid, we are giving another 200 turns conducting wire. So N1 for us is 600, N2 given is 200, L is equal to 1 meter or 100 centimeters. We always take SI units. So R is your radius, that is given as 2 centimeters. We are writing it as 2 into 10 power minus 2 meter. So we have to find out mutual inductance. Before that, you should find out what is the area of the solenoid. To begin that, we have to know one more value, which is mu naught. Mu naught is a constant called relative permeability of free space. That value is given as 4 pi into 10 power minus 7. So we will find out what is area. Area is pi r square. Pi is 3.14. You can substitute it as 22 by 7 as well. So after pi you have to have radius square. Radius square is 2 into 10 power minus 2 into 2 into 10 power minus 2. So if you calculate this value, you will be getting it as 12.56 into 10 power minus 4 meter. After this, you will find out your mutual inductance. So that is the formula for mutual inductance. The remaining is only substitution. N1 is 600, N2 is 200, 4 pi into 10 power minus 7 is your mu naught value, into 12.56 into 10 power minus 4 is your area value. The whole thing should be divided by length, which is 1 meter. I have not done it here. Okay. When you calculate this, you will get 1893.04 into 10 power minus 7 Henry is your SI unit for mutual inductance. So this was your first question. Let us see what the next question is. A 2 meter long solenoid with diameter 4 centimeters and 2000 turns has a secondary of 1000 turns wound closely near its midpoint. Calculate the mutual inductance between the two coils. So it is similar to your previous question. So let us see what all is given to us. Length is given as 2 meter. Diameter is given here instead of radius. So you have to calculate your radius. So diameter is 4 centimeters. Radius becomes diameter by 2. So that will be 2 centimeters. This centimeter, converting it to meter, you will have 2 into 10 power minus 2 meter as your radius. Then you have to remember your constant value mu naught, that is 4 pi into 10 power minus 7. Then you have N1, number of turns in the inner solenoid, as 2000 turns, number of turns in the outer solenoid as 1000 turns. You have to find out your area and mutual inductance. Here you can actually skip the step for area that we are doing here. Even in the previous question you could have skipped the area calculation. That is because this pi r square comes with the formula. As you can see, the next step, there is already a pi r square there. So instead of you solving area separately and putting it back into the equation, you can directly substitute your pi r square in the expression itself. So you will have to substitute. Your mutual inductance M is given as N1 N2 mu naught pi r square divided by L. So as I told, pi r square can be directly substituted, or you can calculate area pi r square separately. So when you substitute for mutual inductance, you will get 2000 into 1000 into 4 pi into 10 power minus 7 into 12.56 into 10 power minus 4 as your area. The whole thing is divided by length, given as 2 meter. So when you calculate this, you will get 1.56 into 10 power minus 3 Henry. The next question is related to your mutual inductance and EMF. So the question is, a current of 10 ampere in primary of a circuit is reduced to 0 at a uniform rate in 10 power minus 3 seconds. If coefficient of mutual inductance is 3 Henry, what is the induced EMF in the secondary? So we have the initial current I1 is 10 ampere in the primary circuit. That current is going to 0. So our final current is 0 ampere. The change in the current that we have to find out, and we have given dt, that is the time that is taken to reduce 10 ampere to 0 ampere, is given as 10 power minus 3 second. Mutual inductance is 3 Henry. So change in current is final current minus initial current, 0 minus 10, so that is minus 10 ampere. We have to find out what our EMF is. So we know the formula relating mutual inductance and the EMF. So EMF is equal to minus M di by dt, remaining is substitution. We have EMF is equal to minus, keep it as it is, M is 3, di is minus 10 divided by 10 power minus 3 is your time dt. So we will just send 10 power minus 3 to the numerator, it becomes plus 3, and minus into minus becomes plus, so your EMF value becomes 3 into 10 power 4. Unit for EMF is volts. Okay, so you write it as small v or just write it as volts. The next question, similar question. In a car spark coil, EMF of 4 into 10 power 4 volts is induced in the secondary when the primary current changes from 4 ampere to 0 ampere in 10 microseconds. Find the mutual inductance between the primary and secondary windings of this spark coil. Okay, so we'll see what all is given to us. It is the same type of numerical, but there you found out EMF, here you have to find out mutual inductance using the same formula. The first one, EMF is given to you, 4 into 10 power 4 volts. Change in current is given to you. I need not explain it again. Initial current is 4 ampere, final current is 0 ampere. So you will have final minus initial, so 0 minus 4 is again minus 4 ampere. Time taken is 10 microseconds. Micro means 10 power minus 6. So you will have 10 into 10 power minus 6 seconds. You have to find out mutual inductance. So we have the formula EMF is equal to minus M di by dt. So M is equal to, keep M on one side, take minus di by dt to the denominator. It will go to the denominator, complete term. Okay, so M is equal to EMF divided by minus di by dt. So substitute the values. You will get 4 into 10 power plus 4 divided by, minus is there, keep minus as it is, di value is minus 4. Then you will have the complete term divided by 10 into 10 power minus 6. So numerator is as it is, denominator you will have 4 into 10 power 5. When you calculate it, that will give you 0.1 Henry. So these are the few numericals that can be asked in the exams. Some will come for 3 marks, some will come for 5 marks. So make sure you all practice such numericals at home.
As we already know, an AC generator is a device that converts mechanical energy into electrical energy. Here are some of the important formulas. Epsilon naught, which is the magnitude of the induced EMF or the peak of the EMF, is equal to NBA omega, where N is the number of turns in the coil, B is a magnetic field, A is the area of the coil, and omega is the angular frequency. Epsilon is equal to epsilon naught sine omega t, and angular frequency omega is equal to 2 pi nu, where nu is the linear frequency. Consider an AC generator consisting of 500 turns each of area 0.01 meter square that rotates at an angular speed of 300 rotations per minute in a uniform magnetic field of 2 Tesla. Find the peak value of EMF induced. Given the number of turns is 500, the area of the coil is 0.01 meter square, the linear frequency is 300 rotations per minute. Linear frequency has a unit of hertz, where 1 hertz is equal to 60 rotations per minute. Hence, to convert rotations per minute to rotations per second, divide it by 60. Hence, the linear frequency is equal to 5 rotations per second. The magnetic field is 2 Tesla. To calculate angular frequency omega is equal to 2 pi nu. Hence, substituting, we get angular frequency as 31.4 radian per second. The maximum value of EMF is the peak value of EMF. Hence, epsilon naught is equal to NBA omega. Substituting for N, B, A and omega, the value of EMF epsilon naught is equal to 314 volts. Consider an AC generator consisting of 1000 turns, each of area 100 centimeter square, that rotates at an angular speed of 100 rotations per minute in a uniform magnetic field of 3.6 into 10 power minus 2 Tesla. Find the peak value of EMF induced. Given the number of turns is 1000, the area of the coil is equal to 100 centimeter square. On converting the area to standard units, the area of the coil is equal to 10 to the power of minus 2 meter square. The linear frequency nu is equal to 100 rotations per minute. On converting rotations per minute to rotations per second, the linear frequency nu is equal to 5 by 3 rotations per second. The magnetic field B is equal to 3.6 into 10 power minus 2 Tesla. On calculating angular frequency omega, omega is equal to 2 pi nu, which is equal to 10.46 radian per second. The maximum value of EMF, or the peak value, is equal to NBA omega. On substituting for NBA and omega, the value of epsilon naught is equal to 37656 into 10 power minus 4, which is equal to 3.765 volts.